Hello, my name is Adolfo Neto, and I'm here to talk about the comprehensive guide to Elixir's list comprehension. So, what is it? The special form, also known as list comprehension. So, we know that Elixir inherited the list comprehension from Erlang, but it has a different name. The syntax is very different in Elixir. And the special form is a construct designed for concise and powerful enumerable transformation in Elixir. So he starts by comparing it to other languages. Let me show here some examples. So suppose you have this structure here. Let me open Ajax. Yes. So you have a list. For every item of the list is a map that associates first name to the first name of some person and last name to the last name. And what's the example of for comprehension here? It uses pattern matching. So for each element of the list friends, you do a pattern matching and get only the last name, and then the result will be a list containing those last names: Swanson, Maffort, and Plostings. You can have multiple generators in Elixir for comprehensions. So, for instance, in this example here, you can, for x from 0 to 99, y from 0 to 99, you generate a pair x, y. So this is kind of a Cartesian product. So it goes from 0 to, it fixes the 0, and then goes from 0 to 99, and then you can see here, but it's going to let me do this. Oh, yes, I can do this. I can say that the Cartesian product is going to be V4, and I can reverse list.reverse. How can I reverse a list? Help reverse. Help list, I believe, no, it's enum.reverse, right? Yes, I can do an enum.reverse with the Cartesian product, and then it's undefined. Oh, sorry, it's enum. And you see that the last elements are 9999, 9998, and so on. So let's continue here. So you can have multiple generators. The generators can be lists like here, or ranges like here. And the counter example using enum map is not nearly as readable as, and demonstrates that you need to remember to flatten the outer loop, or else you get a list of lists. So this is a kind of code smells, right? Let me, yes, you are going to use flat map, and then a map, and then create the tuples. Okay. Generates the same thing, but it's less readable. Generators work with maps too. The comprehension works with anything that implements the enumerable protocol. I believe this is not true, for instance, for Erlang, but I'm not sure. So you can iterate through a map as well. The generator will wield each key value pair of the given map. So here we have a map called dictionary that associates a word to a description. And after that, for each pair word definition in the dictionary, it prints the word and the definition. So this happened because you can see a map as a list of tuples. As it uses IO puts, it returns 3 OKs. As seen above, we can iterate through a range as well. Yes, we have just seen. Bitstring operators. No, bitstring generators. The generators we've seen so far have been list generators. The other type of generator is the bitstring generator. The bitstring generator allows you to easily loop over a bitstring while correctly parsing bytes. For a primer on bitstrings, please see the fantastic guide on elixirlang.org. Yes, and this is often very useful when parsing binary protocols like database protocols. Below is an example that demonstrates that each iteration of the comprehension reads the message length and then use it to know how much more of the bit string to read next. While the previous examples could be translated into various forms of enumap, this example can only be achieved with normal recursion. So this is a bit string. Okay, you type this, but it's internally represented as a binary, and it uses this pattern. Yes, this is the pattern. Yes, it's a pattern where the binary is here, the bit string. And it's going to get message length and message binary size of message length. So yes, this is very powerful. Let me open here. So it gets only the message, but to get the message is here. To get the message, you need to know how many bytes, what's the length of the message, and it gets by pattern matching first with 1, then 6, then 4. Let me try a little experiment here. I'm going to say that this is 2, and now I'm going to, let me see. See, it failed because the data was not correct, was not as expected. This is the same thing, but using recursion. You have the bit string, you apply the for loop to the bit string, and you generate the list by yourself recursively. And this is not tail recursion, right? To compare the two styles, let's look at the syntax of the generator in the comprehension example and the second function head of the loop in the function example. In the function example, you see we pattern match on the bit string in a similar manner to who will you pattern match on a list. We pull several individual items of the beginning of the bit string, this, and we pattern matching on the rest of the bit string with rest binary. here. And in the here you don't need to pattern match on the rest. The list equivalent looks like, yes, if it was a list. Now if we compare this to the Bitstring generator, we can see the similarity with the caveat. The LHS of the Bitstring generator is the pattern matching on the individual items on the right-hand side, and the right-hand side is pattern matching on the rest. The caveat is that Bitstring here is not actually the rest on each iteration. It's still the entire Bitstring. I find this is the best analogy to describe how the Bitstring generator works, since it's different enough from normal list generator. Individual item, rest. This will print the same thing every time. Yes, the for takes care of the part of the bit string that's it's being pattern matched here. Chaining. So this is a long post. I will not continue to read everything here. Let me take a fast look at this one. Okay, two generators, one from... Oh, this is interesting because the second generator comes from the first pattern match. Hobbies and hobbies here. Generators filter non-matching left-hand side values. Yes, so it's going to work only for this one. Friends. And here, oh, this is good because here it works, here it causes an error. This behavior can be useful if you only wanted to iterate over configuration options that are enabled. You could write something like this. Enable true, yes. Filters and options into it's very interesting because you can create a map with into, or in this case I believe he's creating a list from using a list as the into actually doesn't change the behavior at all. Yes, you can, but you can create a map into base map. Here you have a base map and you do a for comprehension and add the results to the base map. Here we can observe three things. The comprehension evaluates to a map. The Mitch key and its value were preserved in the final output, Mitch. And the Greg key's value in the base map was overwritten by the value yielded during the comprehension with the same key. Strings and bit strings, reduce. I didn't know you could reduce. My favorite option to the comprehension is reduce. Let me see an example. So for x, that comes from 1 to 3, reduce to 0, you have a kind of a function here that receives the x and the accumulator and returns x plus the accumulator. It's not working. I believe I have to copy and paste. Yes. There are two immediate things we can observe. First, the reduce option takes a value that's to be used as the first value of the accumulator. Second, the comprehension mode includes a slightly different syntax. Yes, this ACC and arrow args and the right arrow syntax that you see in anonymous functions and case expressions. This is the syntax that allows the comprehensions to yield the accumulator to the block on every iteration. The additional syntax is the same as the other place you have probably seen it. You can pattern match and pass additional clauses. Oh, you can have a for with several clauses. Where is the accumulator here? The accumulator is X and Y? Yes, because it returns a tuple. Position, no, not possible to move. Interesting. Above, we can observe we've written 5 different clauses, pattern matched on the shape of the data, as well as added guard clauses that capture the data in the generator and the accumulator. The beauty of using a comprehension as a reducer is the ability to use multiple generators and act on them as if they are one level of iteration. In this example is simpler. To write this without a comprehension, it would look something like this in unreduced. Yes, this one looks better. Conclusion: if you've made it this far, congrats. The comprehension packs a lot of features into a tiny programming construct, and demonstrating all of them is a lot of work. The comprehension is one of my favorite features of the Elixir programming language, and it was a pleasure to write about every feature in as much depth as I could. If you have any questions, you can go to Twitter. Oh, it has list comprehensions in Erlang too. The Erlang documentation. Thank you, Seth Brown, Eric Ostrich, and Kevin Rankin for their help. Oh, I'm going to add my email later. Here's the Bitstrings. Here is the Mitch Hanberg Twitter account. List comprehensions on Erlang. Yes, I don't see anything about maps because do we have map comprehensions in Erlang? It has a pointer to they say once they are made available. This is funny because we don't have this. Let me try to see if this is available for Erlang. Erlang. I believe it's not, but I'm not sure. So I have a map, and I'm going to try to do a map comprehension. Syntax error. So it seems it's not there yet. Oh, Mitchell Hanberg. He's a senior engineer at SimpleBet, like my friend Herminio Torres. And that's it. Thank you, Mitchell. I didn't read everything here, but I believe the idea was to read a little bit and motivate people to read the full blog post. I hope people get interested in this blog post. See you later.